So we have tackled a general approach of how you can solve any Newton's law problem under the sun. If you're in my class, we've done a lot of harder problems around these ideas. If you're just watching and not really doing any problems, you might be thinking that my examples are pretty elementary and you might not be getting as much out of this as you can. Really, this becomes, right, you realize the strength and kind of this approach when you actually are solving problems. And there are, of course, more forces that we could talk about. Spring forces, we'll come back to that when we do oscillations, right? And there's a variety of other forces I can throw in, to make these problems more and more complicated. But it's the same exact approach. Let me end with a quick little thing on non-inertial reference frames. So what can you do if you just know you are not in a good frame of reference, but you still want to do physics and you would still like to get the answer correct? Again, I think the example we had before was you're driving in a car and you are accelerating towards the right. So this is really the acceleration of the car relative to the ground. And there's an air freshener that as you accelerate, you notice that it's kind of hanging backwards. Though there doesn't seem to be, from your perspective in the car, it doesn't seem like there's anything actually pushing the air freshener towards the back. You do your test of your Newton's first law test. You realize you're not in a good frame of reference, though you do have at least the additional bonus piece of knowledge that you know how your frame of reference is a bad frame of reference because it's accelerating. The entire thing is accelerating. How can you reconcile this? You can fix the fact you're in a bad point of view by introducing fictitious forces. Again, forces that are not true forces or real forces in any real sense of the word. Real as in how I defined them modules ago, and real as in that there's not an agent that's actually creating this force. Really, it's a correction to deal with the fact that your reference frame, which likely is tied in with your coordinate system, is bad. So that you can still analyze motion in your bad frame of reference and get an answer that matches reality, right? You come to the conclusion that yes, the air freshener should move towards the back of the car when I accelerate the car forward. And really this can be understood just by what we know about relative motion. So let's consider the person on the ground. This is the ground observer, which is an inertial frame. They are observing you, which will anchor your coordinate system in your reference frame to you. They're also looking at the air freshener. And so they can say that, yes, there is motion with the air freshener. So this would be R of, what should I call it? I guess we can just use air freshener. So air freshener relative to ground. They are also looking at you, which that might be the car relative to the ground. And then you are observing the air freshener. So this is R of the air freshener relative to the car. And by the relative motion of it all, the position of the air freshener relative to the ground looks like it is the same thing as the car relative to the ground plus the air freshener relative to the car, just by vector addition. Now let's take the derivative of this expression twice. So I can turn these into velocities, I can then turn them into accelerations. So this says that then the acceleration of the air freshener relative to the ground is the acceleration of the car relative to the ground plus the acceleration of the air freshener relative to the car. And again, let's think about what these accelerations tie to and mean. The acceleration of the air freshener relative to the car, that is the acceleration as seen from inside the car. Again, which possibly this observer does not need to necessarily know that the car is accelerating. It's just you look behind you at the thing dangling down and you make an assessment as to the acceleration as you see it in the car. Whether or not, it doesn't matter whether or not you know that the car is moving. This acceleration is the acceleration as seen in the inertial frame. It is this acceleration where that Newton's second law does correctly connect to. So this is equal to F net divided by the m, the mass of the object. Right? The F equals ma only applies in an inertial frame, so it's that acceleration on the left-hand side that connects to the net forces that are acting on the object. So if you wanted to write down Newton's second law in an inertial frame, right, you would say that F net equals the mass of the object times the acceleration of the object or the air freshener relative to the ground. Though we just wrote down that that's the same thing as the acceleration of the object relative to the car, or the air freshener relative to the car, plus the acceleration of the car relative to the ground. What I've written down here is completely true. You could use, because I'm writing down Newton's second law in an inertial frame and writing down my expression here that seems to have two accelerations. But really it's just two vectors that when added together give me the inertial acceleration as viewed from the person on the ground. Let me move m times the acceleration of the car relative to the ground to the other side. So then you get something like F net minus m times a of the car relative to the ground equals the mass times a of the air freshener relative to the car. This kind of looks like F equals ma, but now I have this additional thing on the left-hand side. And again, these are the real forces. This is the acceleration, or the mass times the acceleration, as seen in the car. So if I calculated the value for that vector acceleration of the object relative to the car, that would be telling me the acceleration I perceive sitting in the car looking back at the air freshener as it does whatever. But notice that if I want to use Newton's second law, which so far, again, perfectly valid the way I've written it down, because I've written it down in the inertial frame of the ground. But I might be interested in knowing, if I'm stuck in the car, what does it appear like to me? What accelerations do I in the car see? Well, that's the right-hand side of this expression. Notice I can do that. I can solve for the a of the object relative to the car by introducing this additional term on the right-hand side. This thing here, this minus m times a, I'll drop the subscript, right? It's just the m times the acceleration of the car, relative to the ground, is an example of a fictitious force. A force that's not arising from a real agent in a sense, but if I introduce this bonus term into F equals ma, that is, again, more or less correcting for the fact I'm in a bad point of view, then I will get the correct acceleration as seen from me in the car, the terrible point of view. So if in a bad frame, which again, by that I just mean a non-inertial frame, that the frame is accelerating by some vector a, which could be linear, it could be rotating, doesn't matter. Then don't use F net equals ma, but use F net minus m times a equals, let's call this a subframe. So then this is A sub frame. Then don't use Fnet equals m times the acceleration in your frame, but Fnet minus m times the frame's acceleration. And then this acceleration, then that is equal to m times a, where this a is the as viewed in the bad frame. And that is definitely worth a highlight. So again, you're adding in a correction factor. That essentially is in a sense is a coordinate transformation. It's kind of turning yourself into a inertial frame. But again, you need to know that your frame is bad to begin with. Maybe you don't know that. If I did not know the Earth was rotating, I would incorrectly think that there is some invisible force going on with, what's pushing the apple away from my hand. But if I know that the Earth is rotating, I can calculate that resulting acceleration, because that is an acceleration, because things are changing direction, even if it's doing so uniformly. If I correct for that, then I can, from my bad point of view, toss the apple into the air and solve a more complicated expression that would tell me that the apple should end up next to me and not fall directly back into my hand. The ones that involve rotation, that's a whole chapter in the books, which we probably won't get to, but maybe we'll come back to it. Let me do a simpler example that's more linear. Let's go back to the air freshener. It has some mass m, and suppose you're accelerating forward. The car is accelerating forward, rather. And there are some things, of course, that no matter what frame of reference you're in, everyone better agree on the right answer. For example, you might all notice, and again, this is not even working in anything like relativity or something like that. Like if you're accelerating at a constant rate, you would both notice that the bob kind of leans backwards and then becomes stationary with some angle theta. Everyone should agree on what that angle is. Furthermore, everyone should agree on what, say, the tension in the string is. It does not make sense to say that one person observes a different tension in the string compared to another, because then that might be saying from one point of view the tension's so high the string snaps, where another point of view the string does not snap. You can't have two different realities. The string either snaps or it doesn't. So they better both agree also on the tension. These can serve as kind of tests, or we can use the tension example as a way to test that what I've highlighted above will give me the same answer no matter what reference frame I'm in. So let's first stick with the inertial observer. They see the entire car accelerating by, the car is made of glass, and they measure the angle that they observe the bob hanging at, and they want to measure the tension in the string. They could do this by a force analysis, to which they would say that there is gravity pulling down on the thing. There's a tension that's pulling up and to the right. There's some angle that they've measured. So this angle is also the same thing. And so they might say in the x direction, there's the x component of the tension, which, by the way the angle is defined, looks like it's going to be t times sine theta. And that better equal m times the acceleration in the x direction, or m times the acceleration of the car. In the y direction, they know that there's a tension pulling up. The vertical component is t cosine. Gravity's pulling down. That better equals 0 if the thing is not moving up or down in any way. The inertial observer thinks there is an acceleration in the horizontal direction, even though from the point of view of the person in the car, it's not moving, right? It sees the thing whizzing by. All right, in this case, I could, right, so essentially this says that t cosine of theta equals m times g. I could divide the two expressions, so I could say t sine theta divided by t cosine theta better equal m a car divided by m g. So then that suggests that tangent of theta equals the acceleration of the car divided by g. That determines what the angle should be. Tell me how fast the car is accelerating, divided by g, inverse tangent, boom. You could ask yourself quickly, does that make sense? If the car were stopped, which means it's not accelerating or it's going at a constant speed, the right-hand side is 0. That suggests theta is 0. That makes sense. It's hanging vertically downward. I might want to solve for the tension, in which case I'm going to need to use a right triangle to help me do that. If this is theta, tangent is a over g. Tangent from my SOHCAHTOA days, opposite over adjacent. So tangent of this angle is opposite over adjacent, which then makes this hypotenuse a squared plus g squared. So then if I want to solve for the tension, I might use the top expression where t sine theta equals m a acceleration, or a car rather, where that t equals m a acceleration divided by sine of theta. But sine of theta, going back to that triangle, SOHCAHTOA, opposite over hypotenuse. Looks like then it's opposite over hypotenuse. So it looks like the tension then is given by m times square root of g squared plus the acceleration of the car squared. Again, does that make sense? If the acceleration goes to 0, this just becomes m times g. Everything's vertical, the tension by rebalancing m times g. So all that seems fine. That's the inertial frame. Now in the car's frame, they think that there are two forces acting on the thing, so they can still find the real forces. There's still gravity and there's still tension. But they're going to add in a fictitious force, where if I take the right to be positive, which I should have said before, they can say minus m times the acceleration of the frame, which since right is positive, it just becomes minus m times the acceleration of the car. They can introduce that as an additional force. In this case, since the acceleration of the car is only in the horizontal direction, that only gets introduced in the x direction. So in the x direction, the real force that they identify is that there's t sine theta again, towards the right. But then they're going to add the fictitious force, m times a minus m times a car. Which again, since the acceleration of the car is to the right, which we're calling the positive direction, and it's only in the horizontal, I'll just get rid of that, and it's just minus m times a car. And they look behind, and they see the air freshener just sitting there stationary. So they don't see the stationary speeding up, slowing down, or doing anything. So they think that there's no acceleration of the air freshener in the frame of the car. Similarly, they write down two real forces in the vertical direction. There's no the car is not accelerating vertically, so there's no fictitious force I have to add. And again, they don't see anything moving, so they want to write that down as 0. And notice, if we do a comparison of what the inertial frame said and what the non-inertial frame said, by introducing that fictitious force, in this case only in the x direction, notice these are identical sets of equations. So both the person in the car and on the ground will reach the same conclusion. So this can be very important. Obviously, right, the example of Coriolis forces, centrifugal forces, right? Centrifugal forces are more or less rotation, right? It's centripetal motion. but you're doing it from the point of view of someone experiencing that centripetal motion. So usually the centrifugal forces is just the same as centripetal acceleration, but you throw in a minus sign because of this fictitious force. And again, it's not because there's no real force here. It's just that you're in a spinning frame. So the centrifugal force is, accounting for that. Coriolis is a little bit more complicated. But it's also dealing with Earth's rotation. But it's relative motion on top of Earth's rotation that Coriolis force arises. And this sort of linear motion stuff as well. So